Okay, this is problem 29.11 from homework 8, and it states that the magnetic field at the center of a 1.10 centimeter diameter loop is 2 milliteslas. And for part A, they want us to calculate what is the current in the loop. So I've drawn a little figure here. We have our current, we have our loop of current with our magnetic field going through it. I've shown the direction of the current as well as the direction of the magnetic field, and then the diameter of that loop is 1.10 centimeters. And I've just written out the variables here and converted them for simplicity. So our magnetic field is equal to 2 microteslas, so can convert that over to 2 times 10 to the negative 3 teslas. The diameter is 1.10 centimeters, so we want to convert that to 0.011 meters. And then we are solving in part A for the current. So for this one, we just want to use our equation 29.8 from the book, which is just the magnetic field of a coil. Is that what it is? A coil center, yeah. So the magnetic field of a coil center, because we are calculating the magnetic field in the center of a coil. So we're going to use this equation here, and then we can just convert that to solve for current. So we're just going to be using this equation here. So we're going to take 2 times R times the magnetic field and divide that by the permeability constant times the number of turns in the loop. So plugging that in, we know to find R we just need to divide our diameter by 2, and then the permeability constant we know is equal to 4 pi times 10 to the negative 7 teslas times meters over amps, and then the number of turns is just 1. We just have one loop. If it was a bunch of loops stacked up on each other, then, you know, we could have, an infinite number, but obviously this is just one. So doing the math there, we get our current inside the loop equal to 17.5 amps. And then for part B, they want us to calculate the magnetic field, the distance. Sorry, I'm wording this so weird. Part B, a long straight wire carries the same current you found in part A. At what distance from the wire is the magnetic field at 2 microteslas? So let's just look at this figure here. This time we're taking a long straight wire instead of a loop. And I've just indicated the direction of the magnetic field here just because I feel like that's always a good idea to have an idea of, the direction of everything. So if our current's going that way, using the right hand rule, our magnetic field is going to be wrapping around the current that way. So it's going to come out of the page and then back into the page under there. And so they want us to calculate at what distance is that magnetic field going to be the 2 millitesla strength, and then with that same current that we calculated. So this time we're solving for R. So we are going to be using a different equation here. This time we're going to take the magnetic field of a wire, and that's going to be equal to the permeability constant times the current over 2 pi R. So we can convert that again to solve for R, and then plugging in our variables. Once again, we get R equal to 1.75 times 10 to the negative 3 meters. So that is going to be the distance away at which that magnetic field strength will be the same with the same current as in part A. And tricky parts to look out for in this one, I guess, is just making sure you convert your units. Yeah, this one's pretty straightforward. Ties into what we're learning chapter 29 with magnetic fields and currents.